So what we've been talking about in the complex plane, when I say a plus bi, you go along the real axis A and then parallel to the imaginary axis B. All right? You can think of that as like a Cartesian representation for this complex number in the complex plane. Now, we also will have a polar representation. As you remember, polar, instead of giving over and up, polar tells you how far out from the origin you go and at what angle. All right? Obviously here, r is equal to the modulus of my complex number z. All right? The polar distance to the origin is the modulus of z. Theta is also very special. It is called the argument, of z. The argument of z. All right, now as you've learned before, theta is not unique. Unlike Cartesian coordinates, where there's only a single representation for each point, in polar coordinates, there are an infinite number of representations for a point. So for example, you can imagine the point 3i. All right? 3i could be thought of when we first learned polar coordinates as 3 pi over 2. I'm going to put a little r when I'm looking at polar coordinates. All right? Or you learned that you could write it as 5 pi over 2. Or you might remember that people also wrote it as -3 minus pi over 2. All right? Because it's like you're saying, go in the minus pi over 2 direction, but go a distance of -3. So, you're really going up. All right? Now, in this class, we don't so much subscribe to the one. All right? My modulus, my r, is non-negative. All right, so this one I'm going to kick out. But these two representations are perfectly valid for this same complex number. That's going to have tremendous implications down the road. So it's something that we should keep in mind. The argument like that is not unique. There are an infinite number of choices for the argument. Okay? Now, sometimes that's awkward. So if we want a specific choice, then we're going to use the so-called principal argument. The principal value of the argument is the one that lies between -pi and pi. Okay? And this is given by the capital A, capital argument. Okay? Argument of a complex number, capital, the principal argument, lies between -pi and pi. And that will be unique for every complex number except 0. 0, of course, is associated with every argument and no argument simultaneously. All right. So now that we've got that relationship, let's see how we can transform back and forth between Cartesian and polar forms. All right, A is obviously equal to R cosine theta. B is equal to R sine theta. All right, so that means that my complex number Z will be written as R cosine theta plus I R sine theta. Now, that's often abbreviated, so I could factor out an R, and this will often be abbreviated by looking just at the C, the I, and the S. R cis theta. All right? So we could, for example, write 1 minus I root 3 as, all right, we need to get its modulus first. The modulus is going to be the square root of 1 squared plus negative root 3 squared. So that's going to be 1 plus 3, which is 4. The square root of 4 is 2. And now I need to do cis. All right, and I need to figure out where my angle is, what my argument is. All right, so I would look here. I go 1 over and the square root of 3 down. All right, so 1 over square root of 3 down. That angle is pi over 3. Okay, so I could say this is 2 cis negative pi over 3. Okay, you could also use 2 cis 5 pi over 3. But the capital argument, the principal value of 1 minus I root 3 is negative pi over 3. Okay? One other important thing for us to recognize about polar coordinates is what happens when we do a complex conjugate. All right? The complex conjugate, if I look in the complex plane, let's see what complex conjugate does. If this is Z, the complex conjugate of Z has the same real part, but the imaginary part is negated. All right? So we could say R cis theta complex conjugate is R cis 2 pi minus theta. And that's certainly true, but it's a little bit awkward to have this 2 pi appearing everywhere. All right? And that's one reason why the capital argument is defined in the way that it is. If I'm using the principal argument for Z and Z complex conjugate, then we see that complex conjugation does not modify the modulus, and it changes the sign, the SIGN sign, of the argument, of the principal argument. All right?